Hi, I'm Charles Dillard with Amphenol Broadband Solutions. Welcome to our Fiber 101 training series. In this part, we'll be covering fiber to the home. As you go through this training, the chat will be open. So if you have any questions, feel free to put those in the question section and we will address them all at the end of the training. In this training, we will define fiber to the home and discuss the benefits of passive optical networks. We will compare different fiber to the home architecture as well as obtain a better understanding of fiber loss budgets. So with that, let's get started. Fiber to the X is a term used to describe various optical fiber delivery typologies that are categorized according to where the fiber terminates. Common categories include fiber to the home, fiber to the premises, fiber to the node or neighborhood, and fiber to the curb or cabinet. Oftentimes, fiber to the home and fiber to the premises are used interchangeably. But for this purpose, we're going to use fiber to the home. So let's talk a little bit about PONs. There are different types of PONs. Here we are showing EPON and GPON. EPON stands for Ethernet Passive Optical Network. EPON provides internet voice and video services by using Ethernet packets, whereas GPON stands for Gigabit Ethernet Passive Optical Networks. GPON provides internet voice and video services by using asynchronous transfer mode or ATM, Ethernet, and encapsulation. EPON offers 1 gigabit up and down and up to 32 ONUs per PON, while GPON provides up to 2.5 gigabits downstream and 1.25 gigabits upstream and up to 128 ONUs per PON. Before we take a look at the end devices at the head end or hub and subscribers, let's discuss the optical distribution network. The optical distribution network provides optical transmission path for the physical connection to the ONUs and the OLT. The optical distribution network has a distance of 20 kilometers between the devices. It consists of fiber optic cables, connectors, passive optical splitters. A PON network starts with an optical line terminal or OLT. OLTs can be placed in the head-end hub site as well as in a remote location. Remote OLTs distance from the head-end or hub can be up to 80 kilometers. The OLT coordinates analog and digital signals that are combined into one signal by way of wave division multiplexing, or WDM. This technology separates the data stream based on the wavelength. One wavelength is designed for the downstream traffic and another for the upstream traffic onto one single mode fiber. The OLT sends out data for all of the ONUs together as a string using broadcast. All ONUs on the PON receives all the data and filters all of the data that is unique for their device. This is done with a broadcast signal, as I mentioned earlier. The fiber leaving the OLT terminates at the optical splitter, which connects to the ONUs at the multiple subscribers' home. Fiber distribution hubs are used to house the fiber cable terminations, connections, patch panels, etc. With fiber optical distribution cabinets, technicians can easily access the cables and connection points. In addition to these patch panels, these cabinets also include optical splitter devices. These hubs are NEMA rated to protect against environmental hazards such as dust and dirt, water ingress due to precipitation or submersion, and corrosion. Fiber distribution hubs may be wall, pole, or pad mounted and are suited for multi-dwell units, or MDUs, distribution, centralized, or in a distributed optical network. As mentioned before, an optical splitter allows a single fiber from an OLT port to be split and shared among many subscribers. This passive splitter acts as a combiner to connect all users to the same shared PON port. Centralized splitter architecture usually are configured with a 1x32 splitter. This splitter input port is directly connected to a single fiber to an optical line terminal, or OLT. On the output of the splitter, 32 fibers are routed to 32 customers' home, where it is connected to an optical network unit. Thus, the PON network connects one OLT port to 32 ONUs out in the field. Cascaded splitter architectures may use a 1x4 or 1x8 optical splitter that is directly connected to an OLT port. Each of these fibers on the output of a stage 1 splitter is routed to the access terminal that houses another 1x8 or 1x4 stage 2 splitter. In this scenario, there will be a total of 32 fibers reaching 32 homes. Splitters come in several configurations as shown in the table on the screen. Common optical networks use a 1:32, 1:64, or 1:28 split ratio. However, with a higher split ratio, distances from the head-end or hub site needs to be shorter. We will discuss this a little bit more in the training. An optical tap is spliced into the fiber in order to distribute or direct a certain portion of the signal to a subscriber. Taps take on a more distributed approach compared to splitters. Taps come in several configurations such as 2 ports, 4, 6, 8, and 12. An optical network unit is the device at the subscriber home that converts optical signals transmitted via fibers to electrical signals. The ONU is the DOCSIS equivalent of a cable modem. If several ONUs transmitted data back to the same port on the OLT at the same time, this would lead to performance issues. To prevent that, time division multiple access, or TDMA, is used. TDMA is a technology that allocates the upstream bandwidth to each end user for a specific time period. This technique is handled by the OLT. ONUs use burst mode transmission for the upstream. Upstream packet flow is achieved via bursts, with each ONU responsible for data transmission within an allocated time slot. When an ONU is not within that time slot, the device disables transmission of its optical receiver. In a traditional HFC architecture, the head-end or hub site consists of a fiber transmitter and receiver, cable modem termination system, or CMTS for short, and an erbium doped fiber amplifier to amplify the downstream wavelength so that the video signal can be split and combined with other wavelengths and distributed over a passive optical network. An optical node is strategically placed in the outside plant. The optical node converts light signal to RF on the forward and RF signal back to light on the return. This active device is usually powered by a power supply. Distribution amplifiers are connected on the output of the optical node in order to amplify the signal so that subscribers at the end are connected with a quality signal. Radio frequency over glass, or RFOG, is an SCTE standard that allows existing DOCSIS services to be delivered over fiber without changing the standard equipment in the head-end or at the customer's home. RFOG solution delivers the same video, voice, and data services as HFC networks, as well as the same back office and provisioning systems. Upstream and downstream traffic use different wavelengths on the same fiber, allowing for a much dense fiber backbone. RFOG design moves the node to the side of the customer's home. With an RFOG architecture, a multiplexer is placed in the head-end or hub site. A multiplexer is a device that combines 2 or more wavelengths for transmission through a single fiber. It assigns individual information streams different wavelengths, or portions of an electromagnetic spectrum. It uses 1550 nanometers for upstream transmission and 1310 nanometer or 1610 nanometers for downstream transmission. From the multiplexer, a fiber leaves the head-end or hub site and connects to an optical splitter. Each fiber in a typical RF solution provides signal only up to 32 subscribers. So in a 256 home service area, a telco or cable operator dedicate 8 fibers from the head-end or hub site to a 32-way optical splitter. Notice that when compared to a traditional HFC network, the optical node or mini node is now at the subscriber's location. As mentioned earlier, an optical network unit, or ONU, converts optical signals into an electrical signal at the subscriber's house. An RFOG ONU contains a fiber in and out port, a wavelength division multiplexer, forward receiver, reverse transmitter, a diplexer to separate the forward from the return signal, and an RF out port. A burst mode reverse laser keeps the return noise low by turning the transmitter on only when a signal is detected. Now let's take a look at an RFOG plus PON architecture. Combining RFOG with a passive optical network allows for higher and symmetrical bandwidth. To do so, an optical line terminal, or OLT for short, is installed at the head-end or hub site. An optical line termination device is a piece of edge device for a PON network. OLTs come in 3 flavors: hub, remote, and node. The OLT coordinates analog and digital signals that are combined into one signal by way of multiplexing. Additional wavelengths are allocated for upstream and downstream. In this example, 1490 and 1310 nanometers are being used. In addition to the OLT, a virtual hub or V-hub is installed. A virtual hub, in a sense, replaces a telco or cable operator's typical hub facility. This facility can provide services for nearly 20,000 customers. This device, which can be placed in an optical node housing, is modular and supports several configurations. V-hubs interface with transmitters, receivers, and other head-end equipment. When configured for RFOG plus PON, the V-hub can support 256 homes. Some ONUs will have a PON pass-through for services requiring symmetrical bandwidth. Similar to the RFOG ONU, the RFOG plus PON ONU contains a fiber in and out interface as well as an RF interface, a wavelength division multiplexer, forward receiver and transmitter, a diplexer to separate the forward signal from the return signals, and an RF in and out port. A burst mode reverse laser keeps the return noise low by turning on the transmission only when the signal is detected. In addition, the ONU contains a PON pass-through port for services requiring symmetrical bandwidth from 1 gigabit to 10 gigabits. That brings us to the PON architecture. Simply put, an optical line terminal and a multiplexer is installed in the head-end or hub site, and a PON ONU provides advanced services for the subscriber's location. Some of the benefits of PON include the lack of powering required to operate active devices within a traditional HFC network. Even with the many benefits, there are some limitations with a PON architecture. The distances for a PON is limited to between 20 and 40 kilometers. What we are looking at now is an RFOG architecture that loses around 18 dB at a 32-way optical splitter. An additional 7 dB of optical signal is lost on 20 kilometers of fiber at 1550 nanometers. Add on an additional 1 dB loss at the multiplexer, and our total loss is somewhere around 26 dB. The ONU at the subscriber home is transmitting around 3 dBm of signal. We are hitting now the fiber receiver in the head end with negative 23 dBm, thus giving us the expected link loss in order for the OLT and the ONUs to operate effectively. It is important to determine loss budget with any fiber architecture. Fiber loss budget is the total optical power attenuation due to fiber length, splices, and the amount of connectors that are used. Link budget refers to the amount of loss that a data link can tolerate in order to function properly. The total connection loss equals the splice loss plus the connector loss plus cable attenuation. The fiber cable itself contributes to a large portion of the loss budget. This amount of loss is based on wavelength as well as distance. In this example, the fiber distance from the transmitter is 10 kilometers at 1310 nanometers. The attenuation at 1310 nanometers is 0.35 dB per kilometer. If we multiply 10 times 0.35, we get a total loss of 3.5. Splices and connectors also contribute to the loss budget. In this example, there is one splice that loses 0.3 dB and two connectors with a total loss of 0.7 dB. The total loss of the splice and the connector now comes to 1.8 dB. So now, if we take a look at the total connection loss of the fiber, splices, and connectors, it comes to 5.3 dB. Lastly, if we add a 32-way optical splitter, there are additional losses. In this example, there is 17 dB of loss that needs to be added. And don't forget the connectors at the optical splitter. In this training, we define fiber to the home and discuss the benefits of passive optical networks. We also compare different fiber to the home architectures, as well as gain a better understanding of how to calculate fiber loss budgets. Thanks for attending our Fiber 101 training series with a focus on fiber to the home. Now I need to go over to my computer and open up the chat to see what questions we have. So if you have any additional questions, feel free to put those in the questions section. Okay, so I got the chat open and we're going to take a look to see if we have any questions that come in. All right, so we have one question from Matt, and the question is there a downside to using a 1x64 optical splitter? So most PON networks are designed for a 1x32 optical split. and that can have the fiber link up to 20 kilometers. So if you are using a 1x64 optical splitter, you want to be mindful that the distance from the OLT to that optical splitter will be around 10 kilometers. So great question. And the next question is, how does testing and maintenance change with fiber to the home? So with HFC, I know maintenance tech and fiber technicians are ones that generally did all the testing of the fiber and the splicing. But with fiber to the home, now installers need to be mindful of cleaning the fiber and testing, even though they may be doing mechanical splicing at the customer premises. However, that optical node, in a sense, is now moved over to the customer side of the house. So with that, there's some up training that needs to happen for everyone. So great question with that. We had another question come in. How do EFDA works? This from Jared. So when we're dealing with fiber, there's attenuation associated with it. So in order to amplify the power of the light, we strategically have to put erbium dope amplifiers out in the network in order to re-amplify the signal or the power level. So that way we can extend that network out into our network. So it's similar to how we place amplifiers, out on our HFC with coax giving us our attenuation. So we were strategically place an amplifier in the middle of that network in order to boost the signal up on our high and low carriers. So that way, as the signal go out through our cable line, then we would just place another amplifier to regenerate the level. So it's similar with the erbium dope amplifiers. So great question. What is the another question came in? What is the optimal light levels coming into an ONU? -1 to -6. So I know depending on the manufacturer, there's this range where we want to make sure that we're hitting it with a certain range where we're not damaging the receiver. So anywhere from that -1 to -6 as far as a sweet spot, but the range for ONUs are really about -3 dBm down to -26 dBm. Which another question came in that was similar to that, was asking what is the output from the ONU at that transmitter, and that range is around 0 to 4 dBm of light. And let's see if there's another question. Okay, here's a question that came in from Aaron. How do optical splitters work, and what's the difference between passive versus an active optical splitter? So a passive device simply just means that powering is not required for it. So if you think about the coax side of the world, a two-way or through a splitter. In order for a signal to pass through that, we don't have to power it into any DC or AC voltage. But with passive device, loss occurs with it. The opposite would be with active devices, such as amplifiers or house amplifiers or amplifiers feeding our line extenders and taps in the coaxial world. But they require some type of powering. And in the HFC network, that would mean taking the power companies, say 110 volts, and then we would convert it down to like 90 volts or 60 volts, and then we would use that to power up our active device. So with optical splitters, although there are active optical splitters, primarily most MSOs use a passive optical splitter, so powering is not required. Great question. And let's just double check to make sure there were no more questions. Okay, that seems to be all the questions that came in. Again, with fiber to the home, you know, the benefits of it again is you know, having a fiber from the head end or hub site all the way to that customer premise equipment. It's cutting down on, you know, costs on our networks. You know, noise that could possibly get in, you know, with a traditional HFC network. You know, but the things to keep in mind, like I mentioned before, is that, you know, whereas an installer, you know, didn't really have to, you know, troubleshoot or work with fiber products on our network, there is a big push to, you know, up scale or up train these technicians on how to handle fiber, and you know, meaning cleaning, mechanical splicing, you know, from the optical tap over to the ONU. So if you have any more questions, you know, going forward on this training or fiber training or any other technical training, definitely feel free to you know, reach out to us at our website at amphenolbroadband.com, and you'll find resources available for not just fiber related products but also coax as well. And then also, you know, be on the lookout in about a month or so. Part 5 of our Fiber 101 training, which will cover remote PHY. And just a little teaser on it, whereas with the HFC network that we currently have, you know, we're creating the signal, you know, directly in the head end. So with remote PHY technology, the actual creation of the signal will occur out in the field at the optical, you know, optical node. So we will be replacing traditional fiber nodes with a remote PHY node. And if you want to know how that works, definitely tune in April for our Fiber 101 Part 5 series, Remote PHY. So with that, thanks for attending our training, and we will see you next time.